Thank you. Thank you all for coming. It's amazing to see so many of you here. I guess it's week one and people still have enthusiasm. In 5 weeks' time, there's not a chance that so many people will turn up. I told my wife I was giving the Lama lecture, and she gave me a little good luck gift. Okay, so I am, as you've heard, I'm a theoretical physicist. In the past, I've described myself as a very theoretical physicist. I work on a subject called quantum field theory. Quantum field theory is the language in which the laws of physics are written at the most fundamental level, at least the most fundamental level that we've uncovered so far. Among the many quantum field theories that are out there, there's one that's particularly important, which is called the Standard Model. The Standard Model is the embarrassingly modest name that we give to the greatest theory ever written down. It's a theory that describes every single experiment we've ever done over 350 years of science. It's an example of a quantum field theory. Many other examples of quantum field theories. If you care about cosmology on the biggest scale, you should be working with quantum field theory. If you care about properties of certain materials, increasingly, you should be working with quantum field theory. But my interest isn't in any particular experiment, although I'm going to tell you about one very important experiment in this lecture. Instead, what I tend to care about is the mathematical subtleties in quantum field theory, sort of to look for the things that we don't understand so well, look for the little threads that if you pull them will start to unravel and hopefully give us a deeper understanding of what's going on. And so what I want to do in this lecture is tell you about one of those threads. And looking back over the past 70 years, I think there's a sense in which it's the single most important thread in quantum field theory. It's certainly one of the most subtle things that we've uncovered. I think it's one of the most important. It's also interesting because, and this is where we're getting at the end of the talk, I think there's lots of interesting open problems that we have not yet succeeded in solving. I'll certainly tell you about my failures in trying to solve some of these interesting open problems. So that's where we're going over the next hour. And the theme is very simple, and the clue is in the title. The universe we live in is chiral. And that means that at the most fundamental level, the laws of physics are different when you look at them reflected in a mirror. It's a fact that we've known should do some quick maths, for roughly 70 years. I still find it an extremely surprising fact. If I was a Hollywood scriptwriter, I'd say things can happen in the mirror that can't happen in our world. It's a striking statement about the laws of physics at the fundamental level. So what I would like to do is tell you, firstly, how we know this is true, walk you through the experiment that first revealed it, tell you why it's important, and that's going to have some mathematical flavor to it, why it's important for the subsequent developments of the laws of physics, and then tell you some of the implications that we haven't yet, I think, fully got to the bottom of. That's the plan for the next hour or so. All right, so this story has a start date. And the start date is very particular. It's a cold winter's day in 1956 in Washington, D.C. And it was on this day that the experiment that Chen-Hsiung Wu, who you can see here, it was an experiment she had been designing and preparing for 6 months, but finally, on this particular day, it bore fruit. We even know what the day was. It's quite interesting. The day was 27th of December, 1956. It's interesting because most people are not in the lab 2 days after Christmas. In fact, Wu had a ticket to go back to China. She had a ticket for a boat to go back to China. It would have been her first time going home and her first time seeing her family in almost 20 years. And yet she decided this experiment was too important to postpone. So she went back to the lab. She actually put her husband on the boat and waved him goodbye and then went back to the lab. So I'll just tell you a little bit about the experiment that Wu performed. I am told that it's technically very challenging. I should confess up front, I have no idea how a screwdriver works, let alone how you do an experiment. Conceptually, at least, it's an extremely easy experiment. This is what Wu did. She got a bunch of cobalt atoms, and she watched them die. Now, cobalt dies through beta decay. It decays with a half-life of a little more than 5 years, and in doing so, it decays to nickel, and because it's beta decay, it spits out an electron as it goes. And the trick to Wu's experiment, the difficult part technically, was the following. Before the cobalt atoms died, she had them all spinning in unison. So the nucleus of a cobalt atom spins, it's a weird quantum thing, but more or less you can think of it as spinning much like the Earth spins or a basketball spins. And so she prepared, using magnetic fields and some very complicated apparatus, she got all cobalt atoms, all 10 to the 13 of them, to all be spinning in the same direction, or like this. And then she watched them die. And Wu's result, and it's going to sound very innocuous, but I really think it's the single most important experiment post-war in atomic physics or particle physics. Wu's result was that if all the atoms spin this way, the electrons prefer to be emitted down. That was it. In contrast, if they spin in the opposite direction, that way, the electrons prefer to be emitted up. That was the simple result that Wu found after her 6 months of work that I think it's fair to say turned our understanding of physics on its head in a way that I will try to get across. All right, so firstly, why is it interesting? Why is it important? It sounds so bland and innocuous. The idea is the following. If the atoms are spinning this way, the electrons prefer to go down. Now, if you think back to probably high school, Fleming's right hand, blah, blah, blah. If you think back to high school, how do you describe spin? Well, you take your right hand, and it's important that it's your right hand, and you curl your fingers in the direction that something is spinning, and you look at the way your thumb points. And so the actual result that Wu found is that when these atoms are spinning in a right-handed sense, the electrons want to go in the opposite direction to your thumb. That was the result. Now, it's interesting because had, admittedly for some rather weird reason, Wu been looking at her experiment in a mirror, she would have come to the exact opposite conclusion to what she did. Because in a mirror, the electrons still go in the same direction, but spins get reversed. Right hands turn into left hands when viewed in a mirror. So had she been observing her experiment in a mirror, she would have not written in a paper that said electrons go in the opposite direction to spin in a right-handed sense. She would have said they go in an opposite direction to spin in a left-handed sense, which is the exact opposite conclusion. So that's the very, very seemingly mundane and innocuous statement that the laws of physics look different when reflected in a mirror. There is a handedness to the laws of physics. Somehow you need to know about the difference between right hands and left hands in order to understand what's going on at a fundamental level. So I can put this in context. If you look very carefully at these two pictures, you can see, or you can figure out, which one is the original and which one I flipped using PowerPoint. Who can tell? Yeah, please. Fantastic. Yeah, so there's two bits, actually. There's the writing on the valve handle. Here, you have very good eyesight to see that. There's also Wu's name. It's upside down, but it's clearly legible here. Here, it looks more like some random Greek letters. It's not at all clear what's going on. And that's usually true in our world. If you look carefully at something in our world, you can see writing or something else. You can tell if you're looking at the original or if you're looking at a reflection in a mirror. What Wu discovered is that at the most fundamental level, the laws of physics are exactly like that. If you were to be able to take a movie of some reaction between subatomic particles and play the movie and play its mirror image, by looking closely enough, you could tell which was the original and which was the fake. Laws of physics are different when reflected in a mirror. Okay. All right, so this is Wu's great discovery. And what followed next is the very obvious question. How on earth do you write down laws of physics that have this property? How can you write down a theory that describes our world where it looks different when reflected in a mirror? It turns out to be very, very challenging to do. It took the better part of 20 years for people to write down such a theory. There were lots of half steps along the way. There's a famous paper by Feynman and Gell-Mann. I think it's the only time Feynman and Gell-Mann worked together. It's the reason they fell out afterwards and hated each other from then on. But it wasn't the full story. The full story came only in the 1970s. It was a theory that Steven Weinberg wrote down. and I want to give you some sense about how this works and why it's so very subtle. And I'm going to start with an equation. There are going to be some real equations later in the talk that it would be nice if you could understand. This isn't one of them. I'm going to have no expectation whatsoever that this is something that you're familiar with or you understand. That's why it's in a picture frame. It's in a picture frame just to reassure you that you don't need to fully understand it. Plus the fact it's beautiful, and beautiful things should be in picture frames. All right, so what do we have here? This is the Dirac equation. It was written down in 1927 by Paul Dirac, maybe half a mile in that direction, over in Johns. And Dirac wrote it down to describe the electron. So this is the equation that describes the electron. For what it's worth, this is the electron field. Dirac actually got this wrong. Dirac thought this was a wave function. It's not. This is the electron field. This tells you should differentiate. These gammas are a bunch of matrices. That's really the heart of the equation. And this m here is the mass that tells you the mass of the particle, the mass of the electron that you have to put in. And if you look closely at the mathematics of this equation, you discover something quite interesting. It was actually discovered by Hermann Weyl soon after Dirac wrote it down. What you find is that the Dirac equation almost, but not quite, splits into two pieces. And the reason it doesn't quite is because the mass m here ties those two pieces of the equation together. That means that if you consider a particle which is exactly massless, a hypothetical electron that doesn't have any mass, the Dirac equation really falls into two pieces that have nothing whatsoever to do with each other, two independent equations. Or in some sense, the electron itself should be thought of as composed of two different particles. And these two different particles have names. We call them left-handed particles and right-handed particles. So what's happening with this? If particles don't have any mass, they're necessarily traveling at the speed of light. So a particle that travels at the speed of light, like an electron, will spin, but its spin, as it moves, is necessarily in the right-handed sense rotating that way, or the left-handed sense rotating that way. So all particles, the electron for Dirac's original equation, but one of the great, I think, unsung unifying themes of 20th century physics is that the equation Dirac wrote down to describe an electron actually describes all the particles in the universe. It's the same equation that describes the up quark or the down quark, or with a slight twist, the neutrino. All the other matter particles that we know of in the universe are all described by this same Dirac equation. All of them fall apart into two pieces if they were massless, a left-handed piece and a right-handed piece. So how do we explain Wu's result, the result that the laws of physics look different in a mirror, what's called parity violation? Well, the way this happens is that the left-handed fermions have to feel different forces from the right-handed fermions. Okay? That's the way it works. Wu discovered parity violation using beta decay. Beta decay is an example of, or a manifestation of the weak nuclear force. And so of the three forces, I'm pausing because I don't know what to say about gravity. Of the three forces that are in the standard model, that's electromagnetism, the strong force, and the weak force, it's only the weak force that actually has this property of parity violation. The strong force acts the same on the left-handed and the right-handed pieces. The force of electromagnetism also acts the same. It's only the weak force which acts purely on left-handed particles and does not act on right-handed particles. All right, so this is a little bit of the theoretical background that we need to understand parity violation. But it has some implications, and it actually has rather dramatic implications. So I'm going to tell you two of them, two things that follow immediately from Wu's experimental result, plus quite a lot of mathematical background in quantum field theory. And The first one is maybe the most dramatic of the two. The first implication of Wu's result is that all particles in the world have to be massless. It's a big leap from the fact that the laws of physics don't look the same in a mirror to this, but it's true nonetheless. And the reason is the following. If you take the Dirac equation, it's only when the particle is exactly massless that that equation cleaves cleanly into two pieces. The left-handed part of the particle and the right-handed part of the particle. If you write down a mass so you get something that sort of feels more familiar as an electron, the electron needs those two bits, the left-handed and the right-handed bit, to stick together. Roughly speaking, so that its spin can point in any direction you like and is not correlated with the direction of travel. But it's only for massless particles that it's possible to write down a theory where left-handed and right-handed bits of the particle feel a different force. Now, that seems obviously wrong. And the mass of electrons in our body clearly isn't massless. You know, J.J. Thomson figured this out in 1897. He knew what the mass of electrons was. Mass of quarks in our body, clearly not massless. And yet, it's an implication of parity violation in the laws of physics that particles are obliged to be massless at the most fundamental level. That's one of the results. And it's true. If you look at the equations of the Standard Model, there is no mass anywhere for any of the particles. The mass has to come about through a slightly indirect means, which I suspect many of you have heard of. It comes about because of the Higgs boson. There is no inherent mass for any particle. The mass only comes because particles interact with a third field, or an additional field, the Higgs boson, that endows them with a mass. Somehow that's a loophole that gets away from this idea that parity violation forces everything to be massless. The Higgs is the only way that things can get a mass in such a universe. Okay. So you can see already, I tried to stress that parity violation was a big deal. This is a huge leap. You go from the fact the laws of physics do not look the same in a mirror to the idea that everything has to be massless. That's the way it is. Next implication is even more interesting, I think, at least from a mathematical perspective. And I'm going to try and give you some sense of what's going on here. So the Standard Model is our best theory of physics. And it consists of a bunch of particles, 12 of them in total, interacting with three forces, whose names I've mentioned already: strong force, weak force, and electromagnetism. And when you first look at the Standard Model, and indeed in the 1970s when people first wrote it down, it looks like this horrible mishmash of ideas. There's some particles that interact with some forces and other particles that interact with others, and it just sort of, there doesn't seem to be anything pretty about it. It's sort of everything thrown together in some higgledy-piggledy way. It's only when you understand Wu's result and the implications of parity violation that you realize what's really going on. And what's really going on is the Standard Model is the most beautiful, perfect jigsaw where everything is interlocked together and in fact could not be any other way. This is a rather subtle result that goes by the name of anomaly cancellation. It was first discovered in the 1970s, but it's something that even in the past few years we've been learning more and more about. And I'm going to try to give you some sense of the way this works. Okay, so what happens? You have a bunch of particles, left and right-handed pieces. We've already decided they have to be massless. And now you want to write down a theory where they interact with different forces. And you get to choose which forces. We're going to be in a make-believe universe here. You can write down any theory you like to try and describe the universe that you would like to design. And it turns out that most theories you write down simply don't make any sense. No sense at all. What happens is you'll start calculating, and you do calculation, and you'll spend days and days doing a calculation, and at the end of the calculation, you'll get some result like 1 equals 0. Just total garbage. And what's happening here, it was understood over many, many years, is that there are a bunch of consistency conditions that these theories have to obey. that somehow quantum physics doesn't like things being entirely left-handed or entirely right-handed. In fact, if you were to write down a theory where the forces interacted just with left-handed particles and never touched the right-handed particles, that's a theory that just can be thrown out. It's a theory that doesn't make any sense. Instead, what has to happen is there must be some subtle balancing act between the way the forces act on the left and the way the forces act on the right. They needn't be identical to each other, that's too strong, but there has to be some sense of equilibrium between the forces that the left-handed particles feel and those the right-handed particles feel in order for this theory to make any sense. And as I mentioned, it's a set of rather complicated mathematical consistency conditions that goes by the name of anomaly cancellation. And I would like to give you a little flavor of this by telling you about some work that I did a few years ago. So here's the work. There's various ways to phrase this. Here's the way we chose to phrase it. This was work I did with Nakarin Lohit-Siri, who was my PhD student some time ago. To take the four simplest particles in the Standard Model: the electron, the up quark, the down quark, and the neutrino. Now, they have electric charges, and if you remember, the electric charges are weird. You know, the electron has charge minus 1.6 times 10 to the minus 19 coulombs. It's a stupid unit of charge. We should just say that the electron has charge minus 1. Okay? And if the electron has charge minus 1, the up quark has charge, I should get this right, 2/3, and the down quark has charge minus 1/3, and the neutrino doesn't have any charge at all. That has charge 0. So it seems like this random collection of four numbers that are associated to these charges. One of the implications of anomaly cancellation is that those charges cannot be anything else at all. They're fixed. They're fixed by mathematical consistency alone. You cannot change them. You cannot alter them. They have to be in those very specific ratios. And I can tell you how we phrased this. So this was understood in the 1980s, but I guess 6 years ago, Nakarin and I were just playing, and we didn't really have any goal in mind. We just thought this was interesting, and so we were just playing with the equations. And we set up the following thought experiment. We took those four particles, and we said, well, let's have the quarks feeling the strong nuclear force, which they do, and let's take the left-handed pieces of all particles to feel the weak force, which they do, but then let's assign random electric charges to the four particles and just plug them into these mathematical consistency conditions and see what comes out. The only requirement we made was that those charges should be rational ratios of each other, roughly because electric charge is quantized in quantum field theory. So these should be rational ratios. And by the way, if there's experts in the room, we really did this for hypercharge, not electric charge. So if you know the Standard Model, it's a bit more subtle than I'm saying, but it boils down to the same thing. All right, so we allowed these four charges to be anything you like, and there's a whole bunch of complicated consistency conditions, and as always, when you have a whole bunch of simultaneous equations, you solve some and you get rid of others, and then at some point, and this was the clever bit Nakarin did, there's a very complicated change of variables. And what we ended up with was an equation that we had to solve, which was we had to find three integers, x, y, and z, which obeyed this equation here. Who knows solutions to this equation? Someone shout out. No solution. No solution. Why no solution? Almost. Fermat's last theorem says there's no non-trivial solution. There is one. The one solution is 1 cubed plus 0 cubed equals 1 cubed. Or you scale it up. You can replace the 1 with any other integer. So there's one solution to this, but only a trivial one. There's no non-trivial solutions, but which, as you all know, it's one of the most famous results in mathematics. It's Fermat's last theorem. So what we do is we take that trivial solution, x is 1, y is 0, z is 1, and you plug it back into that complicated change of variables that Nakarin found, and out come the charges of the electron minus 1, the up quark plus 2/3, the down quark minus 1/3, and the neutrino 0. the charges of the 4 particles in our world have to be that way, and they have to be that way because sitting at the heart of the consistency conditions of the Standard Model is Fermat's last theorem. It's an amazing result. I should say this is the baby version of Fermat's last theorem. Fermat's last theorem is really where this exponent is any integer of 3 or greater. You don't have to be Andrew Wiles to prove this one. You only have to be Euler to prove this one. Nonetheless, it's sort of interesting that these consistency conditions are related to what are obviously very deep ideas in number theory that are sitting at the heart of the fundamental laws of physics that govern our world. Those electric charges cannot be anything else. All right, so I hope you're beginning to get the idea of why I'm excited about Wu's result. Wu's result, coupled with what we know about quantum field theory, has astonishing consequences, many of which we're only just understanding today, 70 years later. All right, so that's kind of things that I think are fairly well understood. There probably is more to understand about this anomaly cancellation business. As I say, papers are still being written today about that. But there are other implications of parity violation, which I think that the dust has not yet settled on. There are other implications where we're still puzzled, we still don't really understand how to read these results. And so what I would like to do in the second half of the lecture is tell you about one of these, and maybe towards the end briefly tell you about 2 others. And so this is implication number 3 of Wu's fantastic experiment. And I sort of hope it's going to be a shock to you. It should be a shock. Implication number 3 is the following. You cannot simulate the laws of physics on a computer. Okay? It is a mathematical theorem that says you cannot simulate the laws of physics on a computer. And I don't want to give you the wrong idea that this isn't, it's complex or complicated and the algorithm will just take exponential time to run and we don't have big enough computers. It's much more profound than that. It's you can't even get going. There is no way to write down an algorithm that simulates the Standard Model on a computer. Okay, it's a shocking result. It's a result that I'm deeply unhappy with, but nonetheless, it's true. It was proven in 1981 by Nielsen and Ninomiya. This is Holger Beck Nielsen, who's Danish, and Masao Ninomiya, who's Japanese. I've never met Ninomiya, but I've been lucky enough to meet Nielsen on several occasions. If you've seen Back to the Future, he's kind of like that Doc Brown character. He's got these crazy hair, and he is literally a mad scientist. I think he's a bit of a celebrity in Denmark. My Danish friends tell me that he's quite well known. I'll give you one example. When the LHC first turned on, this is sort of roughly 2010, there were all sorts of engineering mishaps that happened. The kind of thing that, of course, happened when you have the greatest engineering project of all time. There was a magnet that exploded, and there was a blockage in the beam pipe. Nielsen wrote a paper suggesting that this was a message being sent by aliens from the future backwards in time to ensure that we never discover the Higgs boson. Genuinely mad, but also genuinely brilliant and creative and amazing, and this theorem absolutely falls in the latter category. It's a beautiful mathematical theorem. I'm going to give you some attempt, I'm going to try to give you a sketch of the theorem, actually, shortly. I'm going to try to show you what this, how a baby proof of this theorem works. All right, but first let me give you a better sense for what's really going on here. Why can't you simulate the laws of physics on a computer? Well, the first thing to say is it's because of Wu's experiment. The bit of physics that you cannot simulate on a computer is the fact that the laws of physics are not invariant under reflection in a mirror. I had this word in the title and I've realized I'm not sure I've defined it, but chiral. Chiral means looks different when reflected in a mirror. Okay? I've given talks like this before, and what tends to happen is I'm talking in front of a smart audience, and when smart audiences hear something that sounds unlikely, like you can't simulate the laws of physics, that they start looking for analogies in their minds. Well, how can that be? What if you do this? So let me say up front, I do not know of any good analogy for this. It's something that comes, as I will try to explain, when you combine relativity and quantum mechanics and the fact that the universe is chiral, that it violates parity. It's not that you can't simulate anything chiral on a computer. Okay, that's obviously rubbish. If that were true, architects wouldn't be able to design spiral staircases. You know, it's trivial to simulate certain chiral things on a computer. It's impossible, according to this theorem, to simulate chiral quantum field theories on a computer. So what's the issue? The issue is the following. If you take the standard model, take any quantum field theory, it's defined on a space, or more generally what we call a space-time, that's completely continuous. The space in which these quantum field theories live can be arbitrarily divided. You can keep cutting up. You know, space is modeled by the real number line, basically, rather than anything else. Now, I've no idea if that's the right description of space. Seems unlikely if you go to very, very short distances. Say Planck scale, quantum gravity kicks in. It's probably not the right description. Nonetheless, that's the way in which our quantum field theories are formulated. Okay? There's an alternative. And the alternative is that you think of space as something much more discrete, like I have here. You think of space as something like a lattice. So there's various points where particles can live, and between them there's sort of a void that you shouldn't really think about. So particles can live on one lattice site, and they can maybe hop to other lattice sites, nearby lattice sites, but there's no sense in which the bits between the lattice are physical. It's actually a good model of what happens when electrons move inside various solids. They're attached to the ions in the lattice in a solid, and they hop to nearby ions. Now, if you want to simulate the laws of physics on a computer, any law of physics, you're obliged to make space discrete, like this. And you're obliged to make time discrete. Because computers can only deal with discrete numbers, only deal with bits, zeros and ones. They can't deal with real numbers that can be arbitrarily, infinitesimally small. So the very first step that you have to take if you want to simulate the laws of physics is make everything discrete, but in particular approximate space by something discrete. And this famous Nielsen-Ninomiya theorem says that when it comes to the weak force, or indeed any chiral theory, any parity-violating theory, you can only formulate them in continuous space. They cannot be formulated when space is discrete. So you can't even get going. You can't even write down an algorithm to try and proceed. It's just not possible. That's the Nielsen-Ninomiya theorem. All right, now, I made the decision that I might live to regret to try and prove the Nielsen-Ninomiya theorem to you. It's more likely that you're going to live to regret it than I'm going to live to regret it, but we will see. I'm going to need a little bit of quantum physics. Who here is an overly enthusiastic first year and has never seen the Schrödinger equation? Seriously, none of you. If I do Schrödinger equation physics, all of you are going to be, don't be shy. Really? All right, we're going to have fun in that case. Okay, so I'm going to prove the Nielsen-Ninomiya theorem to you. I'm going to prove a baby version. I'm going to prove a baby version of the Nielsen-Ninomiya theorem in which space is not three-dimensional, like in our world, but space is just a one-dimensional line. Okay? Now, we're going to talk about massless particles, and if you're a massless particle moving in one dimension, you have two options open to you. You can travel that way at the speed of light, or you can travel that way at the speed of light. Okay? We call them, I think, entirely reasonably, right movers and left movers. Okay? In our three-dimensional world, the difference or the analogy is the left-handed particles and the right-handed particles, things that spin in different ways when they move at the speed of light. Much more complicated in 3 dimensions. In 1 dimension, it's dead easy. You either go that way or you go that way. Okay? So we have a massless relativistic particle, and what I want to do is just write down for you the relationship between energy and momentum for a massless particle. Okay, if this was non-relativistic physics, it would be energy equals a half mv squared. And then you remember that momentum is mass times velocity. Momentum is p, by the way. For relativistic physics, or massless particles, the relationship between the energy and momentum of a particle is exactly the same as for a photon. Its energy is proportional to the momentum, p, times the speed of light, c. Okay? The only novelty here is this plus sign. So what I've got on the board is the energy-momentum relation for a particle that only goes in that direction. Okay? A particle that is only right moving. And it's a little bit subtle, so I'll try to walk you through the subtlety, but there is a bit of a leap here. So how do you see this? There's a few ways. Firstly, if you know what group velocity is, or you know what Hamilton's equations are, velocity is the derivative of the energy with respect to the momentum. And if you use that definition, you can see that it's always positive simply because the slope is always positive. Okay, that's the first way. If you don't know what group velocity is, or you don't know what Hamilton's equations are, one way of looking at this is that all positive energy particles have positive momentum. So they're all going that way. Of course, this begs the question, how should you think of negative energy particles? This is actually a long story to do with solving the Dirac equation. One of the big surprises in 1927 when Dirac wrote down his equation was that it had solutions like E equals mc squared, but it had other solutions that looked like E equals minus mc squared. And most people in the community actually just threw it away. And there were several years where no one thought the Dirac equation was interesting because it had these negative energy states. There's one exception to that statement, which is Dirac thought the Dirac equation was interesting. Dirac worked for roughly 4 years trying to make sense of those negative energy states, and he came up with what I would say is a fix. And it's not really, now we don't think of this as the right explanation, but he came up with a fix. He suggested the following, that these particles the Dirac equation is describing are fermions, and in particular they obey the Pauli exclusion principle. And so what he suggested was that all of those negative energy states were already filled with some electron C that was filling the whole universe. And so that slightly preposterous idea I've simply shown by having a different color purple in this line. What he also suggested, which was much more dramatic, is that if you take one of these filled states and move it up here, what you're left with is what we call an antiparticle. So this was how Dirac succeeded in predicting the existence of antimatter, was by thinking about these filled negative energy states. It's just worth pointing out, actually, two things. First, that in condensed matter language, these antiparticles are called holes. They exist in semiconductors, exist in other materials. They're very well understood. There's nothing fishy about them. Secondly, if you take one of these states and you excite it, you get a particle which has an absence of negative momentum. But an absence of negative momentum is positive momentum. So that's another way of thinking about why including these negative energy states, is a particle that goes that way at the speed of light. Okay. All right, if that's a particle going to the right at the speed of light, it should be obvious that this is a particle going to the left at the speed of light. And it should also be obvious that this is the description of a particle that gets to choose which way it goes. It can either go to the left at the speed of light, or it goes to the right at the speed of light. Okay. All right, this next point is where we need a little bit of quantum mechanics. And so I'm going to build up slowly. The first thing I'm going to do is tell you what I think is the simplest problem that you first solve when you meet the Schrödinger equation. And you've promised me you've all met the Schrödinger equation. So I'm not sure I believe you. So what is it? I'm not going to think about making space discrete. I'm going to change space in a different way. I'm going to take space to be a circle. And if space is a circle and you have a quantum particle moving on a circle, then the momentum that quantum particle can have becomes discrete. So the momentum is quantized in units of h bar over the radius of the circle, and this n here is an integer that can be, well, an integer, 0, 1, minus 1, 2, minus 2, and so on. So, as I said, you can get this by solving the Schrödinger equation. You can also get it in a slightly simpler way, which is you think about these de Broglie wavelengths and having an integer number of de Broglie wavelengths going around the circle. It's a much simpler way to get this result. Okay, so the punchline here is if space is periodic, space is a circle, momentum is discrete. And the reason I'm telling you this is because there's a more counterintuitive converse statement, which is that if space is discrete, momentum is periodic. So the converse statement, in fact, the correct statement is the Fourier transform of this statement, is that if space is discrete, if space is a lattice, then momentum becomes periodic. If you've studied any solid-state physics about how electrons move inside materials, number one fact about solid-state physics is that the space of possible momenta is a periodic space. But it's weird, and it's a very counterintuitive result. It means that if you've got very large momentum in that direction, and you keep increasing your momentum in that direction, at the end of the day, you end up with momentum in that direction. It's one of these strange quantum effects. I'd say a few more words. It's tempting to think that if you go faster and faster in that direction, you end up moving in that direction. That's not what's going on. What happens is, as you increase your momentum in this lattice environment, to begin with, you go faster and faster, but as you increase your momentum more and more, eventually you slow to zero, and as you increase the momentum yet further, you start moving in the other direction. So that's really what's going on. The relationship between momentum and velocity becomes something much more complicated in the presence of a lattice. Nonetheless, this is what we need. So if space is discrete, as you need to simulate things on a computer, momentum has this weird property that it's now valued on a circle, which means that if we go back to these kind of graphs that I had before, this horizontal axis here actually has to be a circle. And so rather than trying to draw it as coming out of the board, what I'm going to do is identify this point here with this point here. So this thing here, if you move far enough along in the positive momentum direction, you come back on the other side. Very weird quantum effect. It goes by the name of the Brillouin zone in condensed matter physics, this periodicity of momentum. All right, so what does it mean for our chiral particle story? If a particle can move in both left and right directions, the momentum doesn't increase, or the energy versus momentum graph doesn't increase forever. At some point, it bends over, and when you're here and you keep moving, you come back on the other side, and everything is nice and continuous. The difficulty happens if you try to put a single right-moving fermion on the lattice. So this was the energy-momentum relation when space was continuous. But if you try and make space discrete, it's not at all clear what can happen, because if this bends over, it can't suddenly jump back down to here, because that's not a continuous function. And the energy versus momentum relation has to be a continuous function. So at heart here is topology. Although that's such a fancy word for something so simple, I sort of feel bad telling you. If you look at the proof in 3 dimensions, there's some beautiful topology. Here the topology is the following, that if you go up, you have to come back down again. It's literally just that. And so if you take a purely right-moving fermion, and you make space discrete, and you look at what happens, you find an energy-momentum relation that looks like this. You go up, but the graph has to be continuous, and so it has to cross the axis at another location. And what it means is that you started trying to write down a theory of a single right-moving particle, That's this thing here. But the lattice rebels. The lattice just doesn't allow you to do it. And it gives you back a theory that includes a right-moving particle here, but also a left-moving particle somewhere else in the Brillouin zone with a different momentum. It crosses the axis somewhere else. There's another low-energy state, which is what you mean by a particle, but it necessarily crosses in the opposite direction. So if this is right-moving, this has negative slope, and this is left-moving. So if you try to take one of these what are called chiral theories, a theory purely of a right-moving fermion, you cannot write it down in discrete space. Moreover, if you give this guy a force, so you add some, let's say, electric magnetic field under which this guy experiences a force, this particle would experience exactly the same force, essentially because it's the same field. It was derived from the same underlying physics. All right, all of which means if you try to write down a theory on the lattice for the Standard Model, what you get is not the Standard Model at all, but a double Standard Model. You will get, in addition to the left-handed path of the electron, a right-handed piece that experiences the strong force. And in addition to the right-handed part of the electron that you actually wanted, there's a left-handed piece that does not experience the strong force. So if you try to write down a theory on a lattice for the Standard Model, you just don't get what you want. You get a double spectrum of particles in the theory. All right, that's the Nielsen-Ninomiya theorem. And so the question is, what are we going to do about it? I don't like it. I've got to confess, I really don't like it. I don't like it for two reasons. The first is, this is a fundamental obstacle to simulating the laws of physics on a computer. And like the rest of humankind, I'm not smart enough to solve the laws of physics on my own. And we need computers to help us. This is really a limit to how we can proceed in understanding nature. Now, it turns out that we get a little lucky when it comes to the Standard Model. The part of the Standard Model where there's this chiral issue is the weak force, but the weak force, because it's weak is actually something that I can calculate by hand. It's the strong force that binds quarks together that's so difficult that we need serious computing power to be able to do it. So somehow we just got lucky for the Standard Model. But at some point we're going to discover the physics beyond the Standard Model. And if that turns out, as is not unreasonable, that it's one chiral, I think that's guaranteed by Wu's experiment, and two strongly interacting, we're completely screwed. We have no way whatsoever to understand what that theory predicts. Just no way. So that's upsetting to me. The other reason that I don't like this is that, taken at face value, it's telling us that at the shortest distance scales, space must be smooth. It can't be discrete if you take it at face value. Now, I don't know what physics is like at the shortest distance scales. I don't know if space is continuous or discrete when we get down to, say, the Planck scale. And I'm okay not knowing, because that's something that experiments need to answer in the future. It sort of feels wrong that we can have that information from something like this Nielsen-Ninomiya theorem. So I don't like it. I'll put this in perspective. If you really take the Nielsen-Ninomiya theorem at face value, it is telling us that we are not living in the matrix. Because it's not just that we can't simulate the laws of physics. No one can simulate the laws of physics. Now, I don't think we're living in the matrix, but I'm not sure that this should be an argument that rules it out either. Okay, so what do? Well, there's two ways forward. One is that you accept that space-time is continuous. Take the theorem at its face value. I spent this afternoon reading Ether and Matter by Joseph Larmor. It's a little bit out of date. It was written in 1900, and it is, I didn't read all of it, over 300 pages on how the ether works. I would love to know what he thought 5 years later when Einstein just blew the ether out of the water. It's worth saying, he wrote it to win the Adams Prize. The Adams Prize is one of the prizes that Cambridge University hands out for theoretical physics. I can tell you, you need to write something much less substantial to win the Adams Prize these days, but it's a serious book. So this is what Joseph Larmor said in there. The ether, if you believe it, is simply assumed to have all the properties of frictionless, continuous fluid substance. So for him, the problem was solved. Space is obviously continuous. Might be the way. The other way forward is to try to do something about it. Because like I said, I don't like it, but it's also a mathematical theorem, so it's not like I can change it. But there is a history in theoretical physics of having these kind of no-go theorems, things that say something is impossible, and rather than taking at face value that that thing is impossible, what you should do is view it as a beacon to tell you how you achieve what you want to achieve. Because as a mathematical theorem, it comes with very explicit assumptions, and if you want to do better, if you want to circumvent the Nielsen-Ninomiya theorem, you've got to figure out which of those assumptions you can do without. Now, they all seem perfectly reasonable, but one of them, if we want to simulate the laws of physics, has to go. So there has been a very long history, roughly 40 years, of people trying and failing to circumvent the Nielsen-Ninomiya theorem. People have good ideas. Oh, I'll get rid of that assumption, and it looks brilliant, and then they simulate it on a computer, and it turns out just not to work. And so what I would like to report is that within the last year, I have joined the list of people that tried and failed to simulate the Nielsen-Ninomiya theorem. So what happened is the following. This whole thing, I don't know, people got fed up of failing. And so for the last 15 years or 20 years, there's really not been much work on this. I personally think it's one of the great unsolved problems in theoretical physics. How do you simulate the laws of physics on a computer? But people didn't really do much for most of this century. Lots of work in the 90s, but then they gave up. About 5 years ago, people started thinking again about how we might approach this. We'd learned more about quantum field theory, so maybe it was possible to make progress. So there were a few ideas. I threw in some ideas, some ways in which we could make progress. And then I was delighted because 2 years ago there was a paper that claimed success. There was a paper by a joint Harvard-San Diego group who took the ideas, partly ones they'd worked with, partly ones that I'd suggested, and actually simulated it on a computer. It wasn't the standard model, it was just some stupid 1+1 dimensional toy model of the kind we were discussing here. But they claimed that for the first time ever they had a chiral theory on a computer. Massive deal. And I was very happy. And I thought it was so nice, I thought, stupid of me, I decided to reproduce what they did. Now, I don't know anything about numerics, and this required some serious numerics, but happily I know people that do know about numerics. One of them is in the audience, Lorenz Lutens. The other one is Geert-Jan Roos, who was working in Hebrew University. So I think for maybe 2 years now, we've been working just reproducing what that Harvard group did, claiming to have a chiral theory on a lattice. And after 2 years, I am confident of two things. The first is that our numerics are much superior to their numerics. And the second is that our numerics are nowhere close to converging. It's not working. I do not believe this paper that came out 2 years ago anymore. So as I said, I'm now part of the failure community of failures in trying to circumvent the Nielsen-Ninomiya theorem. I should say it might be that these ideas still work. It's not like they failed to work. It's just that they were so complicated that the numerics was not up to scratch to get there. So maybe we could come up with something smarter to do it. But at the moment, this remains, at least in my mind, one of the great open problems in physics. How do you simulate the laws of physics on a computer? There are some related problems, and I'm going to be very, very brief here, and then I'll finish. It turns out there's a collection of different implications, all closely related to each other, that all follow from parity violation, from Wu's experiment, and all slightly similar in spirit. So here are two that I'm mildly obsessed with. There is a theorem similar to the Nielsen-Ninomiya theorem that says our universe cannot have a boundary. Now, again, I've no reason to believe our universe does have a boundary, but I don't want someone to tell me that. I mean, it should be something that experiment decides. The problem is that if you have a boundary, a right-handed fermion will bounce off as a left-handed fermion. It flips the chirality of the fermion. But if they feel different forces, something dodgy goes on, and you can't do it. Again, following the 90s movies reference, this is telling us we're not living in the Truman Show. At the end of the Truman Show, he sails off into the sunset and hits the edge of the world. If we're sailing off into the void, this is saying there's not a boundary to our universe. Okay. There's another statement which might not be a surprise to most of you. It also says you can't have a magnetic monopole in our universe. Now, it might not be a surprise because one of the four Maxwell's equations is an explicit statement that magnetic monopoles do not exist anyway, so why would you care? Divergence of B is equal to 0 says no magnetic monopoles. Magnetic monopole, by the way, is the north pole of a magnet without the accompanying south pole. However, starting with Dirac in the 1930s, I think it's true to say that any physicist who has thought about this thinks that law of physics is obviously wrong, that there are magnetic monopoles in our universe. Dirac found a loophole in the argument that there are not, and subsequent developments show, I think, overwhelmingly that they most likely exist. Let me put it this way. We have the standard model, but anything that goes beyond the standard model, almost without exception, predicts the existence of magnetic monopoles in our universe. So we think they exist, but there is a puzzle because, that again follows from parity violation, about what happens if you scatter an electron off a magnetic monopole. No one knows the answer to this. It remains, again, an open problem. So I think, a little like the Nielsen-Ninomiya theorem, there are ways around this. I don't know if there is a boundary to our universe, but mathematically there could be. And I don't know if there are magnetic monopoles, but mathematically they could be. And when we understand how this is possible, just like when we understand how to simulate the laws of physics, we'll be learning something new about quantum field theory and new about the physics that describes our world. All right, I'll finish there. Thank you very much for your attention.